Hello. Today's topic is conduction, actually, thermal conduction, and we will also discuss rate of flow of heat, thermal conductivity, thermal resistance, and some kind of similar topics. So, this is uh, a burner or some heat energy source, and there is a rod made up of a conducting material or any kind of material. So here we have this end is at high temperature and other end at low temperature. The basic condition for spontaneous flow of heat. So we know that now from source, that is the agency which is at high temperature, heat will flow. So rate of flow of heat, I'm writing it ρφ H is equal to dq by dt. Some calculus notation, otherwise we can also write it q by t. Q is heat, so rate of flow of heat, we can say dq by dt together as rate of flow of heat. Sometimes it is written as h also, but okay, we are happy with dq by dt. So now let us consider a bar, and it's this left end is at th, which is higher temperature, and right end is at TL, which is at lower temperature. Length of this bar is L, and there is a heat energy source. So, and area of cross section of bar is A. So across this area of cross section, heat will flow, heat energy will flow, and so this rate of flow of heat is directly proportional to area. Means larger the area, so greater will the heat flow. And there's another term which is called temperature gradient. dt, capital T for temperature, dt by dx. In some books it is written as d theta, but okay, I will use standard term dt by dx. All right, so this is as I said, temperature gradient, change in temperature with respect to distance. All right, so instead of writing dt by dx, I'll write, because this is not I'm taking a general case, uh, so I'm directly writing, instead of dt I'm writing temperature difference, which is th minus tl upon, instead of dx I'm writing l. So in case if there is some continuity and some kind of variations in t with respect to x, so we can also put that dt by dx also, but in simple cases we can do this. So after removing proportionality sign, we have a constant k, it is capital K, and it is not just any constant, it has a specific nature, it has a specific title for it, and it is called thermal conductivity. So if we set a formula for thermal conductivity, then it will be dq by dt, that is rate of flow of heat, and this term will go in the denominator, simple mathematics. So thermal conductivity is related to how good a body is in terms of conduction of heat. So here it is, K is dq by dt multiplied by L upon A Th minus TL. Alright, so unit of K, okay, we know Q is measured in joule. It is energy, actually heat is energy simply, per second, meter upon meter square. And for temperature there is Kelvin. And now do it yourself, try to solve it, and you will end up with this: joule per second per meter per Kelvin. Okay, you need to memorize this. Sometimes this joule per second is also called watt, so you need to remember that also: watt per meter per Kelvin. So it is all about this thermal conductivity. For material to material, it varies. So here I have considered some materials: silver, copper, aluminium, glass, a common glass, water, and glass wool. So all of these are in SI unit, means that watt per meter per Kelvin. So you can see silver, as we know, it is a very good conductor of electricity. So also it is a very good conductor of heat. So it has higher thermal conductivity, whereas you can see how small value of thermal conductivity is for glass wool. There is another uh, term which is called aerogel. Aerogel, now it is commonly used in space technology and all for thermal insulation. It has very small value. All right, so in terms of this thermal conductivity, can we can understand which material is suitable for faster thermal conduction and which is suitable for insulation purpose. Now let's because I think this formula is a bit complicated, and uh, the application of this formula is appearing bit problematic. But if I correlate it with electricity, it will become easier. So we know in electricity, resistance R is given by rho L upon A. Rho is resistivity. So we know that resistance belongs to any given object, but resistivity belongs to its material. As we have just studied about thermal conductivity, it is also depend upon material of an object. So all right, resistivity is rho, and it is equal to reciprocal of thermal conductivity. There is in electricity, there is conductivity also. We don't study it in class 10th, but it is there in class 12th. So V equal to IR, Ohm's law, we know that. So now in the place of R, we can put rho L upon A. So V is equal to I rho L upon A. Right now I'm just considering this uh, electricity concept, and I'm rearranging this formula. So for I, the formula will be We will do some cross multiplication and then it will be A upon rho L, and then multiply entire this thing by V. So on left side there is current and on right side there is potential difference and some other terms. So so we can rearrange it like this also: 1 upon rho A upon L, and as rho is 1 upon sigma, so sigma is also 1 upon rho. So I'm putting it as electrical conductivity I equal to sigma A by L multiplied by potential difference. All right, so why we have done it? Because it will be easier for us if we correlate it with the electrical um, uh, this electrical analysis with thermal analysis. So okay, further this I is q upon t. So in differential form I am writing it dq by dt, that is rate of flow of charge. So dq by dt is equal to sigma A by L times V. And we know, as we have already discussed, that rate of flow of heat dq by dt is this. So here rate of flow of heat is equivalent to current, and rest of term you can see there is a greater similarity, and you can see this dq by dt is equal to thermal conductivity K times A by L TH minus, or we can write delta T, TH minus TL, which is temperature difference. So see how similar these things are. Here we have K A upon L, we can call it oh sorry, we need to arrange it further, then I will name it. So here again I am writing V equal to I and R. We'll cross multiply this and rearrange this. We know now that the temperature difference plays the same role as potential difference does in electricity, and current plays the same role as in electricity as rate of flow of heat plays the role in thermal physics. So here I'm, instead of dq by dt, I'm writing it h as rate of flow of heat. So here we have V equal to IR, and here we have delta T equal to H RTH. And you can see that this RTH is L upon KA. So as we know that rho L upon A, so instead of rho there will be uh, 1 upon sigma and then L upon A. So we will call it thermal resistance. So in thermal physics, keep this analog in your mind.